Hello, and welcome to a demonstration of the precision image-guided irradiation workflow in MuriPlan, Xstrahl's treatment planning system for the SARRP. I'll be using the example of a brain irradiation to show how to design a treatment plan and then use this plan on the next mouse or subsequent fraction. Throughput is an important aspect of preclinical research, and one option to achieve it without compromising the iteration precision is to carefully create a treatment plan for the first animal in the study, which includes contouring and the evaluation of dose volume histograms, that can then serve as a template for future irradiations. MuriPlan is designed to guide you intuitively through a number of steps in the treatment planning process, from image acquisition to the irradiation. First of all, usually we'd acquire a cone beam CT, and this can be launched directly from MuriPlan by clicking this green cross over here. But since this is only a software demonstration, I've already loaded a CBCT that I had on a file. One important thing to note here is that for multi-fraction treatments especially, a careful and reproducible setup simplifies the procedure tremendously and ensures that plan templates can easily be applied from one mouse to the next. And for brain studies specifically, which I'll be looking at now, the white immobilization bed is very useful. There are a couple tools that I find very helpful that I'll activate right after loading or acquiring the CBCT. One of them is to show slice intersections, which just helps me orient myself when I'm only looking at one of the views. And then in the next step, there is the volume rendering tool, which again is mainly an orientation tool, which allows us to view the animal in 3D to evaluate beam placements and also organ at risk placements. Let me just adjust there we go, and go back to MuriPlan. Finally, as said, I'll be looking at brains, so let me already zoom in slightly so I can look at the head more carefully, and also over here already move towards the head and maybe adjust the contrast and brightness slightly, even though that already looks pretty good. In the next step, there is the option to load a reference image, such as an MRI, for example, for better soft tissue contrast. And also, this is where we would be able to load a template treatment plan. But since this is the first animal of the study, I'll skip this right now. Now we're at the first interactive step. There are two features that I'll be going through. First of all, the segmentation thresholds that assign tissue types to the CBCT, and the contouring of organs of interest. The tissue segmentation up here is very important as it directly influences the dose calculation. So it doesn't look too bad already, but I think this mouse is maybe a little too fatty over here. So I'll just adjust this slightly. So you can see the lungs nicely in this pinkish red. Green is tissue, yellow is fat, and then the bones in white. There's maybe a little too much bone up here that doesn't necessarily belong there, so I'll just very slightly adjust this as well. There we go. The thresholds that I just adjusted over here I saved as part of the treatment plan, and they will differ slightly from animal to animal or even from day to day for the same animal. But since all animals in the same study are typically of a similar size and a similar weight, the saved segmentation thresholds with the plan will simplify the workflow when using a template quite significantly. Now to the next step, creating contours of the organs and regions of interest. This is necessary for a thorough evaluation of the treatment plan. I want to be sure that all of the tumor volume receives the prescribed dose, but the healthy tissue and organs at risk around it receive as little as possible. And in order to contour specific regions in here, I'll use a suite of tools that are, some of them are new with MuriPlan 3.0. Since this is a brain tumor treatment, I'll naturally start with a target first. I have to admit, though, that this mouse doesn't actually have a tumor, so I'll just be basically making one up for demonstration purposes here. You can tell that when you move your mouse over here, it shows up in the different slices. This is really helpful for orientation too. So I'll be moving in slightly, adjusting what I'm looking at, and I'll just pretend that this is where the tumor sits. Maybe add a little more to it on either side. All right. Now, I want to make sure that the whole volume of the tumor is irradiated, and I might have made some contouring mistakes as well. In order to capture all of that, I will first of all duplicate the volume, call this the PTV, my planning target volume, and add a margin to it just to be on the safe side. In order to do that, I'm just going to grow the volume by 1 millimeter isotropically in all directions. And because it has the same color right now, let me just change the color as well. There we go. Nicely grown tumor. The first organ at risk, kind of almost obviously in this case, would be naturally the brain. So I'll do that next. In order to make the brain contouring more efficient, I'll use the interpolation tool, interpolate between slices. This means I don't have to go through every single slice individually, but I can only contour a certain number of slices, and then it will automatically interpolate between them, and I can kind of tweak it, but don't have to do it all again. Let me start up here in the olfactory bulb and just slowly make my way through it. I can increase the brush size as we go along, as this becomes bigger. I'll do a couple slices every now and again. Make sure that I'll cover it all. Here's the tumor, but that obviously sits within the brain, so that will be contoured as well. And I'll go, you can kind of follow it on the bottom panel here, how far back I am, just as an orientation. I don't want to go too far back, start to get into the brainstem, but I think something like this looks pretty decent. You can also, if I zoom in a little bit, see it in 3D over here. Now let me interpolate between slices. I'll preview, see what it does from it. Can scroll through the individual slices, and I have to say that actually doesn't look too bad. There's maybe a little over here that I want to erase. This goes a little too far into the bone for my liking, but that's about it. I will confirm the interpolation, and there we go. There is our brain. Now, from the location of the tumor, if I'm looking at different organs at risk, the oral cavity would be one, but that's more or less up here, so maybe not so relevant. What is a little more relevant, now here's our oral cavity again, if I'm going through it, are the salivary glands that kind of sit and come around here. So I will add that in as an organ at risk as well. Let me just call it glands. There we go. And this one, I'm afraid, is something that I will have to draw manually. This is maybe a little bit too much as well. Let me go maybe to something like this. This is just going to be a pretty rough drawing of the whole thing, just as a guideline to where I really don't want to irradiate. And I will interpolate between slices again and confirm. There is our gland region. As I mentioned, it's really just a rough estimate. It's a bit too hard to see on the CT, but just something that I want to avoid in general. Now, as I mentioned, because we're going to be using this as a template, but also general, it's just good practice to save the treatment plan at the end of every step. They are saved in a date and timestamp format, so they're easy to find again. Now that I've contoured the structures of interest, or the structures that should be or shouldn't be irradiated, the next step is the beam placement. First of all, I'll add an isocenter into the middle of my tumor over here. And it's easy to just drag and drop it around to make sure it sits really centrally within it. I'll just do one in this case because we only have the one tumor, but multiple ones would not be an issue. And I want to give 3 gray per fraction. For the beam placement, there are now a number of options. One typical case would be to do a parallel opposed beam. Let's see what size we need. That actually looks quite fitting. And if I say parallel opposed, I would suggest one coming in from the left and another one coming in from the right. And because this mouse wasn't exactly set up for this specific purpose, it's actually kind of crooked. So I'm not going to use the -90/90 over here, but I'll adjust the beam angle accordingly. There we go. And going through it, I can verify that my tumor and the isocenter are nice and square within my beam. Since version 3, MuriPlan supports both Monte Carlo and superposition convolution dose calculations. Monte Carlo offers a little bit of a greater accuracy, especially at tissue to bone boundaries, but generally comes at the cost of being a little bit slower. So since we're creating a template plan where we want to be very sure of what we're doing, I'll use the Monte Carlo for now and then the superposition convolution algorithm for the next fractions. It takes a moment to calculate, but actually not all that long. And in the next step to evaluate the treatment plan, I look at the isodose lines for the dose distribution. And I'll also calculate the DVH, the dose volume histogram. while the DVH calculated, and now especially, it's already visible that their tumor coverage is pretty good, but there are hotspots both in the bone within the beam path, but also at the skin at the beam entrance. This is also visible in the DVH by the fact that quite a large percentage of the brain actually gets the maximum dose, or 3 gray, while a lot of it also gets no dose, which isn't so much of a surprise in this beam arrangement. Another option would, instead of having 2 parallel opposed beams, would be to do a single arc that will wrap around from one side to the other. In this case, let me see if I can find my glands over here. There we go. I think I don't want to go all the way around in order to spare the lower half of the head of the mouse, especially my glands, but I could go a little further, so a little further than a half arc. So let me do that by moving slightly further down over here and also slightly further down over here. In 3D, this is also clearly visible. I'm kind of at the edge right now. And again, I will calculate the dose. One thing I didn't mention earlier is that you can actually control the statistical uncertainty to which the Monte Carlo dose engine calculates the dose deposition, and a higher dose uncertainty will give a slightly slower computation time. But generally 2% is something that works very well, in my opinion. Now I will look at the isodose lines again. And you can already see that the hotspot is still here because the tumor is a little closer to the surface, but it's gone from the skin surface. It's only in the bone. And let's see what the DVH says. As expected, there's more of the brain, of the whole volume, that gets some dose, but a lot less that gets a very high dose. And of course now the gland region that I contoured does get a very little bit of the dose as well. But especially if you're looking at this over here, there is, because we are only going in from the top, there is very little of the dose that reaches down here. Another neat feature is that MuriPlan will automatically give you volume statistics, both in terms of volume and dose. Now, I personally would say I'm very happy with this treatment plan, but of course it's a trade-off between sparing organs at risk and tumor coverage, and is something that will have to be evaluated in the study design. But for me, I'm happy with my treatment plan, so I will save it again. And then all that would be left to do is to execute and actually irradiate with a beam on time of just over a minute. Now, since this is only a software demonstration, I can't really execute the beam, but let's just assume it's the next day and we're on to the next fraction. So I will start a new session. And normally, of course, I would acquire a new cone beam CT, but in this case, I'm going to load another plan from file. It's the same plan actually, unfortunately, so there are a couple of steps where you have to bear with me a little bit. As you can tell, the process up to here was quite lengthy, and this is not something that is easy to do in a study with many animals or many fractions on a day-to-day basis. So instead of going through the exercise of contouring and evaluating multiple beam arrangements for every single mouse, I will now load the treatment plan that we just created as a reference. This actually does not overwrite the previous plan. It creates a new one that is a copy of the one we just made, but it will load the contours, the isocenter, the beam arrangement, and also the segmentation thresholds. Since this is, as I mentioned, exactly the same scan, the thresholds and the contours do match exactly, but normally from day to day there is a slight variation, so the segmentation thresholds can easily be adjusted to match the next mouse by pulling the sliders, for example. In terms of contours, they just have no meaning from one animal to the next, so I'll just remove those out of here. For the treatment planning, let me zoom in again so I can see my brain a little bit better. Let's assume the tumor, well, if it's the same fraction, the tumor will not have moved, but if it's the next animal, you can easily adjust the location of the tumor by drag and drop, and also adjust the angles of the beams slightly if necessary. Again, by dragging and dropping. One thing I did not do, because I don't think it's necessary in this case, is to run the 3D rendering again, but of course that's also possible. Now, in order to save time, I'll use the superposition convolution dose engine for my dose calculations. As you can see, the time saving between superposition convolution and Monte Carlo for just a single arc isn't even all that great. But I will not skip the verification of my dose distribution. But again, you can look at it, and this is something that I, for one, would be very happy with. Once that is the case, that is it. That is the way how to apply a safe treatment plan as a template for the next day or the next mouse in the study. I hope I could demonstrate how to design a precision image-guided treatment for brain tumor irradiation and how to use the created treatment plan as a template throughout the study. Thank you for listening.